section 10.2, which is calculus with parametric curves. It's building off what we learned in 10.1 where we introduced parametric curves. Again, nothing super intensive with this topic. We're just adding some calculus to it. So do a couple definitions, a couple examples, nothing too crazy here. First, derivatives and tangent lines. So suppose that f and g are differentiable, and then define a parametric curve, x equals f of t, y equals g of t, just like last time. So if we have point x1, y1, we'll correspondingly have f of t1 and g of t1 for our parametric curves given right there. So for a tangent line, to say that's what we're looking for, we would use this formula right there. That's the general formula for a line. However, m is defined as dy dx, so evaluated at xy. So the main thing here is we got to calculate m. That's basically what this whole process with calculus with parametric curves is allowing us to do. Is find an m for something that is different than just a straight line, which you're used to. So to find m, which is dy dx, we use this formula here that dy dx equals dy dt over dx dt. So it's just a fraction of derivatives. So we have derivative dy dt and then dx dt. And then the only condition here is that dx dt cannot equal 0, because if it does, then you have divide by 0 error, and that doesn't work. So that's our only condition. And then we just have a quick note right here that horizontal tangent exists when dy dt equals 0 and dx dt does not equal 0. And then likewise, a vertical tangent exists when dx dt equals 0 and dy dt does not equal 0. So that just means we have like a straight vertical line or a straight horizontal line. That's really all that's getting to there. So nothing super crazy with that. The first example we're going to take a look at here is going to be to find the tangent line to the curve given by x equals square root of t, y equals t squared minus 2t, and then at point t equals 4. So again, we want to find y minus y1 equals m times x minus x1. So specifically, we got to find our m value and our y1 and x1 values. So we'll start by finding our y1 and x1 values. So we know that x1 equals square root of 4. So we're just going to plug in our t value into this equation for y and that equation for x. So x1 square root of 4, we're taking only the positive value here, obviously. So x1 equals 2. And then y1 is just going to equal 4 squared minus 2 times 4. So 4 squared, that's 16, minus 8, that's going to give us 8. So our coordinate point x1, y1 equals 2, 8. So we could really go ahead and plug in our 2 value there, and then our 8 value there rather, and our 2 value over there. Now we just got to calculate m. This is where the differentiation comes in. So m, remember, equals dy dx, which is going to equal dy dt over dx dt. Well, that's going to be taking the derivative of t squared minus 2t, that's our y value, and then taking the derivative of our x value, which is square root of t. So just 2 separate derivatives. This is not quotient rule. We're just, think of it as L'Hopital's rule. You're just taking the derivative of that and then the derivative of this separately, keeping them in that fraction form, which results in 2t minus 2 divided by 1 over 2 square root of t. So this is just going to equal 2 square root of t times 2t minus 2. And that's our m value. So I'll just highlight the important parts here. So we got our coordinate points, we got our m value. So dy dx at t equals 4. Dy dx, this just means that vertical line there, t equals 4, means like evaluated at t equals 4, is just going to equal 2 root 4 times 2 times 4 minus 2. So we're just plugging in our 4 value or our t value, which equals 4, into this equation here, which is going to give us a precise number for m. That's the idea here. So then we just evaluate this. So 2 times square root of 4, so that's 2 times 2. And then we have our 2 times 4, that's 8, and then minus 2. So that all equates to 24. And that's going to equal m. Again, we're getting a precise m value. We're not leaving it as this. So we have to evaluate, we have to plug in and evaluate this at t. In this case, t is 4. Now that we have that, we're just plugging in all these points into our equation that we see right there. So I'll just mark that out. So now plug into equation. And specifically, I'm talking about this one. So it's just plugging in points from here. Y minus 8 equals 24 times x minus 2. And you could leave it like this, although simplifying this out might be a little bit better. So y minus 8 equals 24x minus 48, and that's just going to give us y equals 24, y I wrote 4 there, should be y equals 24x minus 40. And that'll be our final answer. Notice this is in y equals mx plus b form, exactly what we're looking for here. Again, we're taking a simple idea of the equation for a line we see right there, applying calculus to it for finding m. Again, nothing super difficult. You just have to know those formulas and then the process to get to that point. Now, the second thing we want to know is we can do this with second derivatives also. Now, this might be your first time seeing second derivatives. If it is, the way you denote them is d2 of y over dx2. So that 2 there is indicating second derivative. So we're replacing y with dy dx in our equation for the first derivative. So we're taking the derivative of dy dx. So the derivative of our m value, which we calculated like in that first example, it's basically just taking the derivative of our m value. So that's just taking, again, the second derivative of everything we see in that fraction. So our example that we'll look at for this is going to be to find d2 y over dx2, so second derivative at curve given by x equals t cubed plus 1, y equals t squared minus 1. So first we just have to repeat the exact same process we did for the last problem to get our first derivative. Again, we don't need equation for a line here, we're just calculating m. That's really all this question is asking. So first, dy dx, this is exactly like we did last time. So dy dt over dx dt, that's going to be d dt of t squared minus 1 over d dt of t cubed plus 1. That'll equal 2t over 3t squared We can simplify this down by canceling one of those powers of t, so we just get 2 over 3t, and that's our first derivative, and I'll just note that here. First, in case there's any confusion. So that's our first major part that we want to compute. Now, d2 y over dx2, so our second derivative. Now d2 y over dx2 is just going to equal d dt of dy dx over dx dt. So all we're doing basically is taking the derivative again of this top portion. Here we're taking that derivative twice, this one stays in once. So we're just taking that second derivative there, like in this fraction form of the top portion. We don't differentiate the bottom portion a second time, just the top, the numerator. So that's going to be d dt of 2 over 3t. That's our dy dx term that we calculated here. So dy dx equals this. Taking d dt of dy dx, so the derivative of this, then over dx dt. So it's really just taking the derivative of that denominator again. That's all that's going on here. So divided by d dt of t cubed plus 1. Well, we already know that denominator just is 3t squared. Then this numerator, we take the derivative of that. That's going to be negative 2/3 t to the negative 2 for that exponent power. And we'll rewrite this whole thing as negative 2 over 9t to the 4th. Simplifies that down some. And then this is equal to d2y over dx2. And that's our final answer for the second derivative here. So again, find our first one exactly how we did before. That's this circle here is the exact repeat process of what we did in example 1. You get this value. That's our m value for if we were looking for the line like we were earlier. Then for the second derivative, you just differentiate this in our numerator, and then this part is just carried down. We're doing the exact same thing here. Notice the 3t squared. And that's it for the second derivative. Finally, for today, we're going to discuss arc length. It's a little bit different, but still involving these derivatives and everything. So if C is a curve determined by parametric equations, x equals f of t, y equals g of t, those should be familiar at this point. On interval a less than or equal to t less than or equal to b, where f prime and g prime are continuous on that interval ab, and c is traversed exactly once as t increases from a to b. So think about just intervals on a graph, and then c is going to be what's the line, you know, like how that it's traversed as t increases. So remember how we had on our graphs previously, at t value equals 1, we have an xy coordinate, and then at t of 2, we have another xy coordinate. That's the same idea here. So if we can't have repeating lines, is basically what this is saying, over the interval a to b. The arc length of c from t equals a to t equals b is L equals integral a to b square root of dx dt quantity squared plus dy dt quantity squared, and then dt for that integral. So this is, again, it's just measuring the length of your arc, so your line. If we go back to over to the previous section of 10.1, think about this as just measuring this line right here, the length of that line. And this is A and that's B. That's all it's asking. And then it's traversed only once, meaning we're going in one direction and it's never going back over it. That's the idea behind arc length. Nothing super sophisticated with that. So again, we're just dealing with that formula, so all you have to do is plug into that. So for this example, this is the final example we'll look at for today in this section, but we just want to find the arc length of the given curve, given x equals cos of t, y equals sine of t on the interval 0 to 2 pi. So 0 to 2 pi, that's going to be our A, that'll be our B value. So we'll just write here that L, our arc length, equals integral 0 to 2 pi, A to B, of square root of d dt of what's our x, that's cos of t, and then all that is quantity squared, plus d dt of sine of t, and of course that's all quantity squared as well. And then this is dt for our constant integration. So from here, we just got to compute what's on the inside. So 0 to 2 pi square root dt of cos of t, quantity squared, that's going to just be sine of t squared, plus ddt of sine of t squared is just cos squared of t. And then that's all times dt. From here, we just need to note that sine squared of t plus cos squared of t equals 1. So we can evaluate this whole thing under that square root just to be 1. So you gotta remember these identities. They're gonna come up from now till the end of this course. So really making sure you can recall that stuff on the fly is imperative, or else you'd have no idea how to do this. So square root of 1 dt equals 0 to pi, that's just 1 dt. So that's going to evaluate to t, 0 to 2 pi, and then we just plug in our values, so 2 pi minus 0, that equals 2 pi. So this is a very easy integration problem, just as long as you remember that identity. Again, as long as you're able to set this up, this is the basic setup. So if you do end up with something really confusing, as long as you're able to get to that point, you do so, you're technically correct. This just has to be integrated at that point. But hopefully the integration problems won't be super challenging for that. Overall, again, fairly simple section. Just recall that formula for arc length, and then how to find first and second derivatives using the parametric equations there, and finding the equations of the lines, like the tangent lines that we looked at in example 1. And with that, our video for today is concluded.